we tried to use physics-informed neural network to calculate some radiative transfer simulations. And so firstly, we try to calculate a time-dependent light scattering problem. And we use a neural network to represent the light intensity at a given spatial coordinate c and a given viewing angle theta and phi and at a given time t. And here it is our radiative transfer equation. And we have time derivative and spatial gradient, and we have absorption term sigma and emission term. And this emission term is just the light from other angles get scattered into our viewing angle. And this big phi here is the scattering phase function, which tells the probability of a light being scattered in a certain angle. And to solve this equation, we need a boundary condition, which is at z equals 0, as well as our initial condition, which is at time t equals 0. And here it is our simple solution. In this example, we try to simulate a material with 1 light second in the axis, and we try to simulate the light propagate from the lower boundary to the upper boundary within 1 second. And the right panel shows the light curve at different observation points shown at here. And we can see with the increase of distance, the intensity of light is decreasing because more and more of light are getting scattered out of the viewing angle. And we can see the arriving time of the light is strictly observing the speed of light. And when we change our viewing angle to 60 degrees, we can also see most of the light arrive at our observation position without scattering, which results in a discontinuity here. And there are a portion of light arrive before and after the most of the photons. And this is due to the scattering effect. And during these simulations, we developed a collocation point updating algorithm based on Markov chain Monte Carlo. And in this algorithm, we tried to move the collocation points to regions, to some regions in the parameter space, which has a larger error on the partial differential equation. And then we can use this move the collocation points to force the neural network to correct for these mistakes. And in the end, we get such a map projected to 2 dimensions, which shows the position of the collocation points. And we can see there seems to be a line. And this line is just around the position of this jump, which means the neural network is making bigger mistakes around the discontinuity regions, and we try to move the collocation points around this position and force the neural network to correct these mistakes. And because we intentionally move the collocation points to large error regions, comparing to the normal physics-informed neural network, which is shown as the blue curve here, we get a larger loss with the updated collocation points, which is shown as the red curve here. However, when the 2 neural networks, one with update on the collocation points and the other without the update on collocation points, the neural network with update on the collocation points shows a smaller loss which means our method on updating the collocation points can accelerate the training and finally get a more accurate result within a limited training time. And in our second problem, we try to solve the gray atmosphere problem. And in this problem, we try to calculate a time-independent radiation transfer field, in the intensity I here, but we introduce one more input parameter called frequency, which is mu here. And the radiative transfer equation is written in this form. And we don't have the time derivative, but we have some modifications on the absorption and emission term, sigma and j here. Sigma is gray, which means it is independent from the frequency, but the emission term j here is a Planck function, meaning the material is emitting light observing a black body radiation law, which is the function big B here. And because we need to make sure the energy is conserved, the total amount of the absorbed energy should be equal to the emitted energy. And the Ks here is Stefan-Boltzmann constant, and this is the law of black body radiation. And during the simulation, we found calculating an integral inside a neural network is very computationally expensive. So we try to develop a temperature neural network, which trains on this integral equation, and we can control the number of sampling points for the temperature neural network to reduce the computation cost, but still conserve a high enough accuracy. So there are two neural networks for this question. One is the intensity neural network, and this is a physics-informed neural network. The other is a temperature neural network, which seems more like a traditional data-driven neural network, and they are trained together. And here are the structure of our two neural networks. Because we know beforehand the temperature relation, the temperature is more of a smooth and simple function to the spatial coordinate z. We just design a very simple neural network to accelerate the training. And for this question, we actually have a theoretical solution which looks like this. The tau here is a linear function of the spatial coordinate z. And the TEFF here is a parameter we should know beforehand. The Q is a rather complicated function which looks like this one, but sometimes we choose Q equals 2/3, which is also a good approximation. And here are the comparisons between the physics-informed neural network results and the theoretical results. On the left column, these results are trained using the physics-informed neural network with the update of collocation points, as I mentioned in the last question. On the right column, the result is trained using normal physics-informed neural network. And we can see when we are updating the collocation points, we can see the result is more close to the theoretical results, which means our update on the collocation points is really working and helping us to the training. And in our third question, we try to calculate the atmosphere is moving with some very large velocity to some relativistic velocity. And because of Doppler effect, we need to change the absorption term with an additional term, which is the shifted frequency versus the frequency in the rest frame. and so does the emission term J here. And we also try to use a more realistic absorption and emission term, which contains the absorption term of electron scattering and absorption term for the bond-free transition and the bond-bond transition. And these three terms are related to atomic physics. And in this animation, we showed how the absorption term on the bond-bond transition at the left column and the bond-free transition on the right column. And the bond-bond transition is related to atomic lines. And because of the velocity, we can see the line is being blue shifted with the increase of velocity. And the line strength is changing with respect to the time and the density. So in this question, we also did some modifications of our neural network. And this time we have multiple output for this neural network. And the input for the intensity neural network is still the spatial coordinate z and the viewing angle theta and phi. However, we output the neural network as a spectrum, and we try to calculate the intensity at different given frequency sampling points. We did this because in our radiative transfer equation, we do not have an partial derivation term for the frequency. So we don't need to do numerical differentiation for the output of the neural network. The temperature neural network is still the same. And here it is the result. And in this calculation, we use a radiative transfer code called TARDIS to make comparison between the physics-informed neural network result and the theoretical result. And TARDIS is a well-developed radiative transfer code using Monte Carlo algorithm. And the blue curve here is the spectrum calculated from our physics-informed neural network. And the orange curve here is the spectrum from TARDIS. We can see the intensity, we can see the line strength, which is at here and here from our physics-informed neural network is weaker comparing to that in TARDIS. And we missed the emission part of the spatial lines in our physics-informed neural network. And for the line strength issue, it is due to the temperature. In TARDIS, there are two kinds of temperature. One is for the black body emission, and the other is to use to calculate the element line strength. So if we lower the temperature in TARDIS, which is shown in the green curve here, we can get a similar line strength as our physics-informed neural network. And also we try to change our radiative transfer equation to include the spatial symmetric term, which is a gradient term shown as this one. We did the calculation again, and this time we can see in our spatial lines, we can see an absorption term and an emission term. However, the temperature profile in this calculation is quite discrepant from that in TARDIS, because we have one more dimension to diffuse the energy, and the temperature drops more rapidly. We suspect maybe there are some other physics included in TARDIS, and we will try to make up for it. So in the future, we will try to include more spectral lines. And in the previous calculation, we only include the spectral lines from hydrogen, and we will try to include more elements like helium and up to maybe iron. Then we can try to simulate a spectrum more realistic and comparable to a real supernova. And this figure shows the spectrum of an observed supernova as in 2011 IV, and TARDIS and a simulated spectra from the TARDIS program. And to notice, this simulation using the TARDIS program only takes about 1 CPU hour, but in our simulation, the computation time is likely to be 6 hours on the best GPU in this world. So we will try to accelerate our training of the neural network and to see if there is some possibility. And also we will try to include more physics into our neural network. And in the end, because we are using neural network, we can try to run analytical differentiation through the neural network via back propagation. So we can directly constrain the property of the material, and which could help us to accelerate to solve the inverse problem for the supernova simulation. And this is the end of my talk. So any questions?
Thank you, Guy. So this is, this is outstanding work. I should have mentioned that Gisa is a graduate student in the physics and astronomy department here at Texas A&M, and his advisor is Lifan Wang. He's an expert in supernovae, and he's an astrophysicist. We are very happy to have this collaboration, and the kind of work that they're doing here is, I think, is groundbreaking in terms of modeling stellar atmospheres and understanding the processes in these atmospheres through spectra, light spectra, and so there's a lot to do still, but we are very happy to have this effort. And so thank you, Gisa. And Lifan was not able to be here today, right? But this is being recorded, and of course we'll talk about it later. So any questions from the audience?
Hi, Xingzhuo. This is the Hao. Thank you for your presentation. May I have the technology slide 12? I have a question about the relative atmosphere. Yes, so I guess slide 12. Yes, and the results. You have the result for no this one. Next one. Yes. So for this one, I'm just curious. So it seems like for this TARDIS, you have the 2 spectrum, and you also have like 2 temperature, right? And it looks like the prediction from pings agrees very well, quite well with this the original curve rather than this the green curve. But on the other hand, the temperature from this ping agrees well with this the green curve rather than this origin curve. So it seems like there is a mismatch from here, right?
Yes.
So what is the possible reason? Is because like you didn't add the complete physics, or is because from the couple of the physics? What's going on?
It is because of the physics inside the TARDIS. In TARDIS, there are 2 kinds of temperature. One is called temperature, the other is called the electron temperature. And we suspect when calculating a black body spectrum, which is the continuum shown here, the temperature used in TARDIS is the electron temperature. But when calculating the level population of elements, which is directly responsible for the spectral lines, the TARDIS is using this temperature. But in our physics involved neural network, we have only one temperature.
I see.
And that's why I run two TARDIS simulations. One is to use to fit the black body spectrum, and the other is to fit the atomic line strength.
I see. Thank you.
Yeah. So I think we may be the only group applying, neural networks to this kind of work. I mean, of course, there are other papers on radiative transfer, and there are other people look into radiative transfer, pins for radiative transfer. But with this kind of application to astrophysics, I think it's probably we may be the only one.